He obtained his PhD in 2019 in Rutgers, and his research area is mathematical models for biology and traffic flow. And Ryan, he's an undergrad student in Rutgers, and is currently working in Professor Spiccoli lab with some research in traffic flow. Please, you can start.
Okay, thank you for the introduction, Teresa. You can all see this, right? Okay. So I guess I want to talk to you first about what I'm going to show and what we're doing and what we did for the summer experiment in Nashville regarding circles. This task, the task I'm talking about was the scenarios team, the experimental scenarios team. And what we wanted to do was figure out the simplest way we could reliably get the information that we were looking for, the most reliable way to get measurements that we're interested in. And if there was any sort of extraneous details in a proposal for an experiment, we would weigh heavily in on whether or not they can be removed, just so that we strip down the experiment and make it as simple as possible, sort of like Occam's razor for experimental design. So one thing we started talking about as our weekly brainstorming sessions was a way to have a protocol for when we start a test and when we end a test, or when we abort a test. And I'm going to tell you what we tried to plan and what we ended up really doing instead. In a lot of cases, for practical matters, we made adjustments and changed up what our plan was. But we had envisioned something like, all right, well, we have several teams that we need to all be ready to go before the experiment starts. What order should those teams check in at? Well, we can't drive cars if the cars aren't ready, and we can't capture everything we need to capture if the surveillance team's not ready to see it. Then we want toward the end of the process, the risk management team to tell us if we're still good to go. And then we would make sure that we had all the drivers ready to go to the cars once everybody else was ready. In reality, the green light protocol was more heavily handled by risk management, by Professor Dan Work. And it involved, each time we went out, it involved a 10-minute safety discussion with also, exactly reminders of what we were going to be doing. We lined up and ordered how we were going to drive so that it was spatially present in everybody's mind, what order the cars would be in. During this risk management pep talk about safety, some people would be doing final preparations on the Raspberry Pis that were loaded in the cars and the RAV4s. And so basically we ordered it pretty nicely, but it turned out to be something that the risk management team had to be hands-on with, basically to make sure that, to drive home the point that safety was the most important thing. And so the green light protocol was mostly a talk about safety beforehand. The red light protocol, what I called the red light protocol, is basically the procedure we would go into if there was some sort of issue or problem or safety risk. Basically, we made it clear that anybody should, let risk management know if they thought there was a safety concern. And so we did have this chain of command set up for aborting a test should something happen. And luckily, we were pretty fortunate, and the worst scenario happened to be an unrelated accident that clogged up some traffic, and we aborted the experiment. So then after we thought about what happens the day of and how to plan it and how best to get the kinds of results we were looking for. We tried to think about, well, if there is something that needs to change, who should be in control of those decisions, who should talk to whom. We made sure that this being pretty big and having a lot of moving parts in the experiment, we wanted to make sure that all the tasks were effectively partitioned in the sense that, well, each team has a set of responsibilities and they will take care of those responsibilities. And only if we need to sort of involve other people do we really have crosstalk between teams. This ended up being pretty important as there was so much to do with regard to the flashing the drives to change the controllers, and even editing some of the software to change the controllers for a more favorable next test day. Fell to the hardware team and the algorithms team, and they worked together on that. But yeah, everybody had internal jobs that they outlined, and not many big changes happened during the test day. So I'd say that it went pretty well with respect to this. We made sure that there would be somebody on every team to record any decision-making processes that happened so that we would be able to go back and revisit this documentation when we, write papers and stuff. We need to know where we were coming from. So I guess the teams we thought, once we had the drivers in position and once we had the idea of what the test bed would be, we had to decide, all right, well, what kinds of teams do we really need? Well, we definitely need a hardware team to handle the vehicles. We definitely need to have somebody understand what we're trying to achieve on the surveillance team. This is Professor Zeibold. We definitely had to make sure that we knew where all the drivers were coming from and how they felt. And that was Maria Teresa, headed the driver management team. As I said, Dan Work was the one to make us realize at every moment safety was all of our responsibilities. And this worked out so well in practice with all of the drivers. And during the actual vendor test there, I had done a lot of planning beforehand. That's what this is about. And so I was basically just assisting with all other teams. So that was kind of the best case scenario for us, we thought. So we know what road we're doing the test on, but we don't know exactly where the congestion is. And so the next phase, I would call it, of this planning the scenario was trying to figure out which part of the road we really needed to get our AVs on to smooth traffic. We need a certain type of congestion. We need a certain type of stop and go waves in order to act on the traffic in a favorable way. So we used example drives where data was recorded of the drive. And what you see here is some drives done at Vanderbilt that were showing what parts of the road were most heavily congested. This does not show waves. You need kind of your speed as it pertains to time for that. But what we are seeing here was where the congestion happens on the road. And this was advantageous in a way, well, very advantageous to help us figure out what part of the test bed we needed to be on at what time. So what you see here is the test bed, and all these blips, all these red dots are the possible starting points. So we used the previous data to figure out where the traffic was going to be most heavy at the times of the drives. So our test bed was westbound, which is to say it basically goes toward the dot that's labeled 1 toward the green dot. So northwest is the direction that we drove on. And the most heavy traffic was found near the caution symbol before Bell Road, between there's 2 cameras there. that was the area of a lot of congestion, and we had a small window to catch it. So, there was a lot of emphasis on planning for the right times here. Um, also, we needed to catch measurements of this action that we were trying to achieve on the traffic. And so the question became, where do we put the drone as part of the surveillance team? There were lots of TDOT cameras that you can see pictures of on the road here, but they were very low res, and we can't control the direction that they're facing. They weren't the best surveillance devices, whereas our drone captured some amazing pictures. And my teammate and colleague, Ryan Delorenzo, who's about to talk now, was able to work out a system with our drone pilot, who I should thank, Murad, who worked with TDOT and was able to collaborate with us. So, before I hand it over, let me talk about a couple more things. So the thing I didn't really get to yet, which is how exactly the formation of the cars would be. This is one of the main things that our scenarios room worked on. And we came at it from an idea of like, what is our ideal? Our ideal is an experiment where we can measure the traffic before each AV and after each AV, and then eventually see the propagation of any wave smoothing effects as they go upstream from the congestion. So that top scenario 1A and scenario 1B, these were the two scenarios that we planned for these two lanes. We didn't do any tests in the far left lane, which is a high occupancy vehicle lane in the actual experiment. But these were our ideals. And we also had a thought about a second scenario, what we called scenario 2, which would be a multi-lane experiment with cars in each lane. And what I want to explain now is that we, for several reasons, we simplified this. It takes fewer cars if we just have one human-driven car, a rental car, between all of the AV cars. Each red one is an AV with running a controller, but also with a driver. When we did plan this, we planned to not have passengers, but we found pretty immediately that it was beneficial to have a passenger, using the ham radios that we use to communicate with each other. And this turned out to be pretty essential for a couple reasons. One, the person driving can't really operate the ham radio. You have to hold it and push a button. And we thought about a scenario where they were always just on and the driver just listened to any emergency chatter. But it was much more useful to be able to have a passenger in each car that could communicate. The second reason why a passenger was good is for all the red AVs, the passenger was able to look at a computer, at a laptop that was showing periodically the speeds that the controller would recommend if it was engaged. And this allowed us to sort of screen the controller's output before we said, all right, ready to engage. The system, I was in control vehicle number 9. And the system, me and the driver is Matt Nice, came up with was, well, when the output of the controller is between +1 and -1, I will give him a green light, and then he'll tell me when he engages it, and then I'll record that time. So that was something else that we never planned because we're only going to have one person per car, but it ended up being a lot better with passengers. So okay.
Right.
So go ahead, Ryan. Yep.
Thanks. So this is the schedule that everyone followed once the experiment week started. Generally speaking, we try to get to our main HQ, the ISIS building, at 6 a.m. This building is on the bottom left of our slide here. And here we took roll call and passed out our safety vests. Once everyone arrived at the ISIS building, we drove the experiment cars to the retail space, which is this middle picture right here. And at the retail space, everyone settled in, and the plan for the day was told to everyone, as well as the safety briefings. This would generally take about 30 minutes. And our final step was to send everyone out to their respected cars that they're already assigned beforehand, which we can see on the bottom right picture. The cars were parked in such a way that once they pull out, were already in formation and ready to be driven onto the I-24. And for the most part, we aimed for 3 tests a day, and we did get 3 tests a day during our experiment week. And but this was a very general schedule. The earlier we got onto the I-24, the better. This was because the earlier we got on, we were able to drive in the early morning rush hour, this was the traffic we were aiming for because it was much more dense and had the waves we were looking for. Next slide. And this was inside the retail space as a video. You can press play. We had a little snack corner in the, we can see in the video right here. We also had a little resting area for the drivers for in between the tests, some bathrooms in the back. And we had a lot of screens in this retail space. This is where we kept everything overnight. The screens would allow our hardware team and surveillance team to hook up their laptops to be able to process data in real time during the experiments. You can go to the next slide now.
Sorry.
So here are some more pictures of the retail space. In the top left corner, we have the surveillance team, and their primary goal was to spot our vehicles as they drove past the T-Dot cameras on the I-24. This would help us, after all of our experiments, to patch together one very long video for each test that followed our platoon as they passed each T-Dot camera. On the bottom left, we see our hardware team working, looking at the data after every experiment and patching the controller as needed in case any bugs were found while we were driving on the I-24. And the last picture is just another general overview of what we were working with. So some changes that were made during the week of the experiment. The first one was, what height do we fly our drone at? Our T-Dot contact came with us with 2 heights that we could have flown the drone. One of them was 200, another one was the maximum of 400. We ultimately decided on the 200 feet one, just because, as you can see in the 400-foot picture, it captures traffic that we don't necessarily care about on different roads. We were mainly focused on the I-24. The 200-foot camera shot allowed us to be able to see each car in each lane on both sides, and this would allow us to spot our platoon very, very easily, which obviously helped in post-processing, as we said before. Next slide, please. Thank you. Some other changes that we made was when the drone was to be launched, and it was decided that once all the platoon, once all the cars were on the entrance ramp, I would send a message to Murad, our drone contact from T-Dot, to send up the drone. This ensured that the drone's battery didn't die during the experiment, and that it will capture the whole platoon and some of the effects of our platoon in the traffic after. Some other ones was adding a passenger to every car, which Sean talked about. It was a very big factor in safety. It allowed the driver to have 2 hands on the wheels at all times and allowed the passenger to just deal with the radio communication and activating and deactivating the controller. Another thing that Sean talked about that we decided to change midweek was running the controller in read only. Again, it was to ensure that the controllers were activated safely, just in case this will prevent the controller to be activated and then a sudden deceleration to occur. And we also used the police to escort the whole platoon into the driveway. Originally, we had planned that they would just take us to the stoplight before the highway, but instead they actually escorted us up to the entrance ramp. This was a great benefit to us because we wouldn't have to worry about public cars or people walking out into the road or anything like that. You can go to the next slide. Finally, some driving behaviors that we changed was firstly, again, making sure the controller was not activated in an unsafe environment. Another big one was the lead vehicle. We decided that the lead vehicle should actually mimic the car in front of it. This was because before, our lead vehicle driver, Will, was a very good driver, and it was a bias. We found it to be a bias for the platoon behind, or in actuality, we wanted our platoon to drive as if it was in everyday traffic with the crazy antics that happens during the morning rush hour. And finally, we decided that instead of giving each driver special instructions to merge into their lane, we just told them to do whatever was felt to do the natural process of merging. This definitely helped us a lot because it prevented drivers from being confused, and allowing them to naturally merge at their own pace worked out every time to be prepared and for the experiment. And I think that should be everything.
Yeah, that's it.
Yeah. Thank you, guys.
Yeah,
very much.
thanks so much. And if you have some questions for us, please ask.
I guess no. Well, if not, let's thank again the speaker. And now this is the break, and we resume soon.